This section is on measuring matter and the introduction of a unit that we will see a lot the rest of this year called a mole. So when it comes to counting particles, both atoms and molecules, it turns out there's a lot of them. So a convenient way to discuss the amount of matter, well, we have to try to package this in a smaller number, something that's going to make sense. It's kind of like it's easier to sell eggs by the dozen rather than individually. If you go to the grocery store and you start putting single eggs on the checkout counter, it would take significantly longer. So they just sell them by the dozen. And when we start talking about the number of atoms of something, we don't say individual numbers, okay? As chemists, we actually need to put an easier way to package that together. So we've created a unit called a mole. So again, it's kind of like talking about a dozen eggs rather than individual eggs. We talk about moles of atoms or moles of molecules. It makes more sense. It's an easier number to deal with because we're going to see that these particles are on the range of like 10 to the 23rd, 10 to the 24th, and that is just a whole bunch of zeros. And so it's not a convenient way to measure them. So instead we use moles. Okay, so what is it? A mole is the SI base unit used to measure the amount of a substance. If you remember back from our first unit, we said there were 7 base units, and one of them was the mole. And I said, then at the time, you may not have heard of this before, but you are going to become very familiar with it by the end of the year here in chemistry. And so here we are seeing it introduced for the first time, mole. What is it? Well, it is exactly what 12 grams of pure carbon-12 is in terms of number of particles, okay? So a mole, it's a counting number. It's not how much something weighs, okay? It's not the size of it. It is just how many of them are there, a counting number, like a dozen, right? A dozen would mean 12. Okay, so what is a mole? Well, it's the number of particles that are in 12 grams of pure carbon-12. And that number turns out to be really large, all right? And you'll want to put this in your notes and star it, box it, highlight it, whatever you need to do. Okay, it's 6.02 times 10 to the 23rd. So you don't need to memorize the full number there with all the decimal points, but you should know the 6.02 times 10 to the 23rd. Okay, this one right there. That number, okay, that number has a special name that is called Avogadro's number, after the Italian scientist that determined it, 6.02 times 10 to the 23rd. So how large is that number, and why is it so big? Well, it's because there must be a large number. It must be such a large number to count such small particles, okay? 12 grams of pure carbon-12. 12 grams is not a lot, all right? That is a very small actual, in terms of size and weight, has 6.02 times 10 to the 23rd atoms in it, okay? Let's say instead of carbon atoms, it was, marbles, right, which are 5/8 inch in diameter. If you had a mole of marbles, okay, not carbon atoms, but if you made those atoms the size of marbles, it would cover the Earth's surface 4 kilometers deep in marbles. Okay, that's a very, very large number, and it really does illustrate just how tiny these atoms are. So this number is so big because the particles are so tiny. So when it comes to visualizing them, water, it is going to form, right, molecules, right? These are 4 covalent substances. We've talked about that. The name of those are molecules. When it comes to single elements by themselves, we are going to refer to those particles as atoms. In this case, right, this is copper, right, Cu. Here we have water, H2O. When it comes to ionic substances, okay, ionic compounds, we refer to those as formula units. So things like sodium chloride there. We would refer to the single unit as a formula unit, all right? But that would be if you had a mole of these, right, you'd have 6.02 times 10 to the 23rd water molecules. If you had a mole of copper atoms, it'd be 6.02 times 10 to the 23rd atoms of copper. And if you had a mole of sodium chloride, you'd have 6.02 times 10 to the 23rd formula units of sodium chloride. So now we need to learn how to convert between moles and the number of particles. And this goes back to some stuff that we learned back in Unit 1 on a section called Dimensional Analysis, which I believe was Section 5. So we're using conversion factors, right? Remember, we could write conversion factors as, right, x over y could then also equal y over x. This would be like 12 inches is the same as 1 foot, and 1 foot is the same as 12 inches. And the unit we would pick, the conversion factor we would pick, would be the one that would cancel units, right? Okay. That's the goal here, right, was to cancel units. Hopefully you remember that section. If not, go back and take a look at it. So when we need to convert stuff, here is our conversion factor, right? 1 mole, and let's go ahead and fix this so that it doesn't look wrong here, okay, is 6.02 times 10 to the 23rd particles per 1 mole. Okay, we could also write that in reverse. We could say 1 mole is the same as 6.02 times 10 to the 23rd particles. Okay, remember that particles here can be atoms, if we are talking about just a specific element. They can be molecules, if the substance is covalent. And they could be formula units if my substance is ionic. So keep those straight. Okay, so here we are just seeing this together, right? We could have either one of these as conversion factors. And the one we're going to pick is the one that's going to cancel the unit that we were given to start with. Okay, so let's say we have 2.27 moles of sodium. And it wants to know how many atoms of sodium is that. And by the way, when we start writing these units, we want to make sure that we write them with as much detail as we possibly can. So we'd say moles of Na, moles of sodium, right? Well, I don't know why I wrote an equal sign. I should be writing a multiplication sign, right? Times. And since I'm getting rid of moles, that's going to be the unit on the bottom. 1 mole is 6.02 times 10 to the 23rd. And in this case, since it's a single element, we are talking about atoms, okay? And when it comes to writing things with your answer, you definitely need to include significant figures. Here we have 3, here we have 3, so my answer is going to have just 3. And this would be 1.37 times 10 to the 24th atoms. Okay, that would be the answer there. Example 2, 1.17 moles of H2O. Being as descriptive as possible when I'm labeling my units, 1.17 moles of H2O times, okay, I'm trying to get rid of moles, right? I should have crossed this off up at the top, but here we go, right? Moles are going to cancel, okay? And I'll be left with atoms, which is what we want. Down below, when we go to do this, same thing. Moles are going to cancel by putting moles on the bottom of my conversion factor. And on the top, we'll have 6.02 times 10 to the 23rd. Now, this time, it's not atoms. I have a covalent substance. So I'm talking about molecules, right? That's what that last slide was talking about there towards the end. So we have 1.17 times 6.02 times 10 to the 23rd to, once again, 3 significant figures, 3 here and 3 here, and it's a multiplication problem, so my answer should have 3. This is 7.04 times 10 to the 23rd molecules, right, would be the answer there. Okay? Now, if we're going in the reverse here, this problem says I have 9.27 times 10 to the 24th molecules of C6H12O6. How many moles is that, right? So this is like saying I have 527 eggs. How many dozen eggs is that, right? Similar type of question. Well, start by writing down the number with a unit with as much detail as you can possibly give. Molecules of C6H12O6 now multiplied by, okay, the conversion factor this time, right? These are my particles. I'm trying to convert 2 moles. So what I'm looking for, the unit I'm converting to goes on the top. So the 1 mole goes on the top here. And the 6.02 times 10 to the 23rd. Now, we could write particles or molecules. I'll write molecules because those are meaning the same thing in this instance. So we have 9.27 times 10 to the 24th divided by 6.02 times 10 to the 23rd. And I should have 3 significant figures in my answer again, and that will give us 15.4 moles, okay, of C6H12O6. Do be careful. When you're plugging this into your calculator, you should write 9.27. Use your E function, 24 divided by 6.02 times 10. Oops, go back and fix that. E23, okay, and it'll give you 15.398 something, okay. Make sure you're using that E function, or if you're not going to do that, make sure that you write this 9.27 times 10 to the 24th in parentheses, and the bottom number 6.02 times 10 to the 23rd in parentheses, okay. If you don't do that, you're going to get the wrong answer. Okay, so make sure you're using parentheses if you're not going to use the E function, right? Which is the second and then the comma on a TI-84. Here are some more for practice if you need them.